the disturbances within the system. This could be caused due to the pipe not being completely filled with fluid or other disturbances that will need to be investigated. Red.
Ryan, did we give you a clap?
Yes.
Oh. Huh? Hello. Would you rather pick someone that's not doing the same thing?
Hello, my name is Ben Kegley. I'm presenting on behalf of the Red Team, who also includes Austin Nilly and Brandon Ennis. We are presenting on the flow system, which is filtered wash system. It is based in, first, here's an outline of what I'll be talking about. I'm going to be going over some of the system information, some background, theory, my results, and data, conclusions. Our system is based off of the sewage plant that is here in Chattanooga. We have a pump that is used to clean the filters after it separates any sludge from the lines so that it can be the clean water or semi-clean water can be put back into the river. These are just feedback controllers, and then we have the option to have valves open to allow water to manual washing stations. This is an example of our steady state data. What you see here, we have an overshot when the input first goes into the system, and then we have an output when it reaches steady state. And this is a block diagram of our system. Our standard steady state operating curve showed that we have a slope of 0.6 pounds per minute per percent of input, and our operating range was 31 to 43 pounds per minute, and that corresponds to 61 to 82% input. This is again the same block diagram of our system, but in the step response theory, when the input is increased in a unit step pattern, the output is delayed until it reaches its steady state again. This is one example of a step down in our data. The circles show weird behavior that was excluded from analysis, and we just kind of started at the parts where it gets done, and that the dip right there is again weird behavior that we left out, and so we had to run a different trial. This is a step up, and all the further analysis will be step ups. But we have here a change in input and change in output for the step, and if you take the ratio of those, you can find your gain, and the gain in this experiment was 0.6, which I would like you to remember our steady state slope was 0.6, which corresponds to that. Our dead time in our system, which is the time it takes for the system to respond to the input, was 0.6 seconds also. That can be found by finding the slope of our increase in output and finding the distance between the time where the input was given. Our time constant is found by finding 63.2% of our output, our change in output. That value is for when the output equation, the E is to the first power, which makes T over tau be 1. So tau here is 0.9, which is our time constant for the system. Some results. This is our system gain. You can see here our steady state slope, which corresponds to about the average of all of our gains in the low, medium, and high regions. Here's our dead times. We have rather large error or uncertainty in our dead times, which it varies from trial to trial, but noise in the system basically is what's going to account for that. Our time constant also has large fluctuations. That just depends on the system and the various trials that are run. In conclusion, we have our steady state operating curve slope is 0.6 pounds per minute per percent. That corresponds to our system gain. And then also our dead times have dead time and constant is relatively low uncertainty. Agreed.
He's got it.
Good, okay. Okay.
I'm John Thetford. I'm on the green team along with Jesse West and his team, and we are the pressure spray booth system. I'm going to give you a little bit of the background about the system, show you my results of the data with the steady state operating curve along with the step response, and say my conclusion. John Thetford. The system is modeled after a system found in a plant in Dunlop, Tennessee. It deals with painting the engine housings, and each of these booths is pressurized. And ours dealt with both of the dampers being closed, which means it mainly focused on booth one. And each of them was always filtered to the EPA standards along with local pollution controls. And when we would run the experiments, it was done by a variable speed blower, which is down here. And we would set an input percentage due to the power, and we hope to get the output in centimeters of H2O within our parameters, which was between 5 and 35. This is the box diagram. We have an MT, which is the input. It's in the motor power percentage, and it would go into the pressure system and come out with your output, which is in centimeters of H2O. This is an example of our pressure constant. This is around the median of all of our data, and input was at 50%. Get the output, which is around 17, 16.5 around. And we got this data with all the trials we ran, and you'd have our inputs right here, and we got the averages doing the sum of X over M. Then we did the standard deviation, and through that we used the standard deviation multiplied by 2 to find the uncertainty, which you'll see in our graph. This is our steady state operating curve. For some reason, unbeknownst to me, around the middle area, we had some, it was just lacking, I guess. I don't know. I really can't tell you why the data was not quite as linear as some of the others, but the points still seem to be just fine. Next we have the step response. This is for gain. What we did is we had a 10% in change from up to down, or down to up, whatever. And then we had our change in output. And when you put the output over input, we got our gain, which was at 1 centimeter of H2O over per second. Next we did our dead time. And the dead time was from the last state of steady state from the lower all the way to the tangent line, and that ended up being just 1 second. By the way, these are all just for the lower. This is not the actual whole group, this is just for lower as an example. And next we calculated tau, which is what we did was we took from the dead time and we had the 63.2%, and our tau ended up being just 0.3 seconds. And this is our graph of the gain. This is all, once again, just for the lower. As you can see, for the lower, there was just a difference of 0.1 in the data from the averages of all the lower up and then to the lower down. But the uncertainties were all matched at 0.1. For our dead time, we had the same value at 1 second for all the averages of the up, along with the step down, with our uncertainties being the same at 0.1 as well. Then for our tau, we had the same for all the averages of the step up to the step down at 0.3 seconds, but for some reason, the step down had double the uncertainty at 0.2. For our experiment, we had the range operation. We put it was between 30 and 70% to get our desired output between 5 and 35 centimeters of H2O. For our gain, we had 0.95 centimeters of H2O. For our dead time, 1 second. For tau, 0.3.
Let me give you some information about what I want from you. John mentioned that he didn't understand why something or other happened. You remember that, John?
Yes, sir.
What was it about? I forgot.
It was our steady state operating curve in the middle area.
Why it has some funny things.
Yeah,
The job is not to explain things in here, it is to describe things. The system is a mystery to control engineers. We don't know why it does what it does. Our job is just to know what it does.
Okay, my name is David Dawson. I'm presenting for the gold team, which is Chris and Clay. We were assigned to the pressure control system, and this presentation will be on the steady state operating curve and step response. So first I will go into just a little background of both the system and the project itself, and then touch on the theory behind the experiments, and then present our results and conclusions. So this is the paint spray system. You see our
Push the button again, and don't push it again. It stays on.
So this is a motor with a blower that supplies pressure to these 3 booths for the paint spray system. And we have 2 dampers that can be used to shut off pressure to booth 2 and booth 3. And so the motor is controlled, percent power to the motor is controlled, and then again, the pressure can be shut off to these booths. The main reason I wanted to show you this is the way, look at the way our system actually mimics that. And so again, we have the 2 dampers here. We have our motor with a blower, supplies pressure to the system. And these dampers here can be open or closed. So as for Gold Team, we were assigned pressure ranges of 18 to 30, centimeters of water with both of the dampers open, which is equivalent to saying that there was pressure supplied to all three of the paint booths. And so the way the system is set up, we can have a manipulated variable. It controls the percent power to the motor. This is our system, and then the output will be some pressure of water. And so our steady state operating curves, we needed to find the mean outputs for the particular inputs, and then plot that output versus the input, determine the best fit curve, and then that function could be used to predict an output for a particular input. And here is an example of one of our steady state experiments. You can see it reached what I would call steady state very, very quickly.